Hello, we are Ignacio García, Zahie Mahmoud, Pablo Cachón, and Alba Hernánez. We are students from University of León, and we are going to introduce you to our work about creating land cover maps with hyperspectral remotely sensed data in the wetland area of Doñana Natural Park, using the spectral angle mapper algorithm. First of all, we will give a small introduction of the study area and the remote sensor used. Then we will explain the materials and methods used for it. And finally, our results and conclusion about the land cover maps. Doñana Natural Park is one of the most important natural reserves in all Europe, because of its marshes and wetlands biodiversity. In 1964, it was born as a place for endangered animals refuge, near the city of Huelva, in the south of Spain. In this work, we have used remotely sensed data from CRIS sensors, developed by the European Space Agency in PROBA-1 satellite. This sensor is useful because its 19 programmable spectral bands from 400 nanometers to 1500 nanometers in the visible and near-infrared spectrum. It obtains images of 13 kilometers per 13 kilometers with 17 meters of ground sampling distance, getting it in 5 different angles: -55, -36, 0, 36, and 55, and also in 5 different modes, where mode 2, water bands, the one used here, has been used on other works for making specific wetlands maps like Smith et al. In 2010. The main goal in this work is creating two 1 to 50,000 scale land cover maps of the study area with a CRIS image. Followed by a wood workflow as an important issue, we try to obtain the best results in two ways. The first one by training areas or regions of interest, and the second one by extracting members using the pixel purity index implemented with our training areas.
The study area is 160 square kilometers of wetlands in Doñana National Park. It is formed by Odiel Marshes, the city of Huelva, Punta Umbría Juniper Fields, and Domingo Rubio Swamp. A hyperspectral image from CRIS sensor was used. The acquisition date was April 12th of 2013, with the identifier that you can see in the slide. This image was taken in the mode number 2, the specific one for water applications. It has 17 meters of spatial resolution and 18 bands from 406.1 nanometers to 1050.5 nanometers of spectral resolution. We have used the nadir image 0 degrees to avoid the problems caused by the sun angle. Two orthophotos from September 19th of 2012 have been used for improving the training and validation areas. Also, the Korean land cover from 2006, it has been a useful implement. The software tools used were BIMBSAT 4.11 version for the noise reduction and top of atmosphere reflectance, and MB 4.7 version for the rest of pre-processing issues, the processing and result validations. The land cover definitions are shown for herbaceous, brushwood, crops, treewoods, soil, water, buildings, roads, sandy areas, and wetlands. First of all, we have reduced the noise, correcting the stripping and dropouts in the image. Then the radiometric correction was done for obtaining top of atmosphere reflectance. The algorithm used was the one you can see in the slide. The atmospheric correction wasn't possible because CRIS Mode 2 image hasn't got enough information about the water vapor column. The last step of pre-processing was the dimensionality reduction using the minimum noise fraction transformation. The image used to have 18 bands, and finally, for an easily working, we took just 13 bands. On one hand, we select the training areas, region of interest as homogeneously as possible and taking all spectral range by class. Then we have used the spectral angle mapper algorithm for the classification. On the other hand, we use the pixel purity index for obtaining the n members. It makes a comparison between them and the spectral library created from our training areas for getting some distinguishable classes. The separability between some classes wasn't so good, so we decided to use our same training areas of the first method for supplying the rest of the land cover classes. Finally, we use the spectral angle mapper algorithm like in the other method. Once we made the classification, we need to prove our results. Taking some truth ground pixels in the image, we create the confusion matrix, calculating with it the producer's accuracy, the user's accuracy, and kappa statistic. In the last step, we obtain the confidence interval by the adjusted Wald method in a 95% of reliability for its accuracy and land cover class.
Classifying with the first way, not all the image pixels were joined to a land cover class, as you can see in the map. There were also some difficulties to differentiate some classes like roads from wetlands and sandy areas from buildings. Using the second method, we have obtained the showed map. All pixels were classified, but it shows the same difficulties to differentiate land cover classes. Afterwards, we analyzed the results from the accuracies, kappa statistic, and confidence intervals of both classifications. We can say that both of them are meaningful with respectively 85.5% and 80.91% of total accuracy. However, the confidence intervals of each land cover class are quite wide, so an improvement of the training and validation areas will be necessary. In addition, the kappa statistic is better in the training areas map than in the member extraction one.
We can conclude that although the second method should be the best one, it hasn't been because the lack of spectral libraries from field data collections. And all the accuracies and confidence intervals should be better with more precise training and ground truth areas. To better differentiate the types of vegetation as water from wetlands, it is recommended to use other hyperspectral image with more near-infrared bands and some others in the middle and thermal infrared. And that's all. Thank you for your attention.